If an aeroplane is in steady flight, then the resultant force on it is zero. Here are the four forces acting on it. The force T, the thrust, acts at an angle alpha to the path of the plane. The path is the dotted line. The lift force acts in a direction perpendicular to the dotted line, to the path. The weight force acts vertically down, which means it's perpendicular to the horizon line. The drag D acts in a direction that is opposite the direction of the flight. That's the flight path. So D is along the same line as this dotted line. Now we are just dealing with a simpler situation of vectors in 2 dimensions here. Now we could call the resultant force on the plane F. Now I'm using this notation here, but of course the underlying notation is what is used in the notes that I'm using mostly, but whatever you want to use, it doesn't matter. Okay, so it's the vector sum of these 4 vectors. So we could just write it like this, and by Newton's second law, that's equal to the mass of the plane, which we can say is m, times the acceleration of the plane, which is another vector. But since the plane is in steady flight, its acceleration is 0. That means it's flying at constant speed in a straight line. In other words, it has constant velocity. So this path is meant to be a straight line, and it's moving at constant speed along that straight line. So that means that A is 0. So we have mass multiplied by 0, which is 0. So the resultant force on the plane is 0. That means if we take the components of these forces in any particular direction, the sum of the components of these forces in that direction will be 0. It doesn't matter what direction we take. The sum of the components of the forces in that direction will be 0. Now we are going to consider forces, or the components of the forces, along the direction of the path of the plane. So we're going to get the component of the thrust force in the direction of the path. Well, that's just the magnitude of the thrust force, which we'll say is T without the arrow, multiplied by the cos of alpha. So that's the magnitude of it. Well, we can take directions along here to be positive, and vectors pointing in the opposite direction to be negative. So for example, vector D is entirely along the path, so we'd write minus D for that vector. So even though these look like magnitudes, we could also think of them as vectors, where the signs give the direction. So there's only 2 directions to consider now, either directions along the path in this direction, the direction of flight, or directions along the path in the opposite direction, which would be negative. Now, what about L? Well, L has no component along the path, because L is perpendicular to the flight path. So, you could say L cos 90. Well, the cos of 90 is 0, so that's going to give us 0. Now, what about W? Well, W is a vector that's at 90 degrees to the horizontal, to the horizon. What about this angle here? Well, the angle in here is beta, the same as this angle here. So these angles are a pair of opposite angles. So that means that this angle here is 90 minus beta. So if we resolve W in the direction of the flight path, well, we're projecting the tip of W onto the flight path. So we are going to get this vector here. Now what's its magnitude? Well, it's W cos 90 minus beta. And since it's pointing in the direction opposite to the flight path, we make it negative. It's a negative vector. Okay, so its magnitude is W cos 90 minus beta. But if this angle is 90 minus beta, then this angle here must be beta, because we've a right angle triangle here. So we're resolving W in the direction of the flight path. We just project perpendicularly the tip of W onto the flight path. So if this is 90 minus beta, this is beta, because these 2 angles must add up to 90 degrees in this right angle triangle. So the cos of 90 minus beta is actually the same as the sine of beta. See, the side opposite beta is what we're looking for, this vector here. So the sine of beta is the vector we're looking for divided by the magnitude of this vector W. Okay, so we have minus w sine beta here. So this is the sum of the components of the four forces in a direction along the flight path, and that must equal 0. So in a sense this is a vector equation, but we're just dealing with one-dimensional vectors along the flight path. So there's only two directions to consider, positive or negative. Which we decide is positive doesn't matter. We've decided to take the direction that the plane moves in to be positive, but we could have made it negative, and then the other direction would be positive. But of course it's important to realize that these quantities t, d and w are magnitudes. They're positive quantities. They're the lengths of the vectors. Now we could also consider the components of the four forces in a direction that's perpendicular to the path of the airplane. So perpendicular means along this line here, a line that contains L. Now we can take this direction to be positive if we like. Directions pointing away from the plane, up from the plane, along this line here. Then that means that directions this way are negative. Okay, so what is the component of L in this direction? Well, it's just L. It's L cos naught if you like. The angle between L and this direction is 0, so L cos naught is just L. And it's positive, so you can put in the plus sign to emphasize that if you like. That's the convention we're using for the direction. This is direction is positive, the other direction is negative. What about the component of the thrust force along this direction? Okay, well, if we just indicate the two vectors that sum to the thrust force, well, here's the component of the thrust force along the flight path. All of this vector here, that was t cos alpha as we saw before. But this vector here is t sine alpha, and it's pointing in the positive direction. So it's plus t sine alpha. Now what about the drag force d? Well, the drag force lies along the flight path. So it's perpendicular to this line here. So it's d cos 90 if you like, but the cos of 90 is naught, so it is no component perpendicular to the flight path. What about w? Well, we're looking for this component here. This is parallel to this line here. Well, that's just w cos beta if you like. This side here is adjacent to angle beta. But notice it's pointing in this direction here. It has to by the triangle law. We want to add this vector onto this vector here to get the vector w by the triangle law. So it's pointing in the negative direction. So it's minus w cos beta. So again we have a vector equation here, but L, T and W are positive quantities. They're magnitudes. They're the magnitudes of the vectors. But since we're only dealing with one direction, as I said already, this direction up this way is positive and the direction down this way is negative. Well, we're dealing with two directions, but vectors along a line. Vectors in just one dimension. Now suppose we want to find the magnitude of the thrust force, that is the force provided by the engines, and also the angle that the plane must deliver the thrust at, the angle alpha, to the flight path to keep the plane in steady flight. So obviously we need the other details, L, W and D, and also the angle beta. So we're given the flight path, so we need to find the angle between the flight path and the horizon. Well, we need to be given the angle between the flight path and the horizon, which is beta. So we're given the mass of the plane, 70,000 tons, and from the mass we can get the weight W of the plane. Well, the weight is mass times g, acceleration due to gravity, which is 9.81. We're also given beta here at 6 degrees, so we can plug that in. So we're looking at this first equation now. We are given that the drag is 130 kilonewtons, or 130,000 newtons. So from this information we can find t cos alpha, and we can also find t sine alpha. So we have two equations in two unknowns, and if we just divide t sine alpha by t cos alpha, we get sine alpha over cos alpha, which is tan of alpha. So we can find the tan of alpha. And once we know alpha, we can find t. Now I just need to make a correction here. This should actually be kilograms. No, sorry. Well, we could leave it as 72 tons. So a metric ton, one metric ton is 1,000 kilograms. See, everything here is in newtons. See, we converted 130 kilonewtons to newtons. So mg, the weight must be in newtons, so the mass must be in kilograms. So if the plane is mass 72 tons, then in kilograms that's 72,000 kilograms. We multiply by 9.81 meters per second squared, so we get the unit of newtons here for the weight of the plane.